machine learning and crystallographic symmetry. All right.
Well, thanks for having me. It's been really fun, and I've been, really enjoying all of these talks. As one of the relatively few sort of computer scientists here, and then I'm going to probably embarrass myself in a bunch of different ways. My physics is kind of like, I don't know, it's like ask ChatGPT about physics, right? It sort of like appears to know what it's talking about, but if you scratch the surface, you sort of discover that it doesn't actually know anything. So when I say dumb things about physics, then I apologize in advance. So I'm gonna tell you about some work that I've been thinking about lately about sort of machine learning and space group symmetry. So I'm calling it crystallographic symmetry to kind of summarize things across different dimensions. But that's essentially what I'm gonna be talking about. And I'm gonna start out in a little bit of an unconventional way and tell you about kind of like the history of like how this project came into being, because I think it's kind of has a sort of a funny origin story. And for that story, I want to rewind you to 2020. And we all had different activities that we undertook in 2020. Watching the Tiger King, and baking bread and hoarding toilet paper, and I did all those things too, right? But another thing I did is I worked on an art project, and my art project was, I thought, wouldn't it be fun to try to come up with generative models that created the kind of like Escher style symmetries, right? Like these really cool tilings. And try to think about how would we make random functions, say, that exhibit these kinds of symmetries. It's just for fun, right? So nothing sort of like super sophisticated. Again, like the sort of like you put your head back in that sort of pandemic times. We all did weird things, and this is one of the weird things that I thought about. And these are, of course, so Escher made these woodcuts, right, of 16 of the 17 so-called wallpaper or plane groups. And so these are the 17 groups that are kind of all the ways that you can tile the plane in some sense with a sort of a single shape. That shape isn't unique and so on, but really what these are subgroups of the isometry group on R2. And you can think about like a set of operations. Obviously, translation is kind of the main one, but also reflections and rotations and glides, which are reflections and translations simultaneously. And when you do that, you get all of these different guys. And so I thought, okay, well, wouldn't it be neat to sort of come up with a way to have to take one of these groups and be able to generate functions that have these kinds of symmetries. And and so, they come up in a lot of different ways. Obviously, Escher is kind of the most famous one in some sense, but they're all over the place. Things like brick patterns. And this is just like a rug in my house that I noticed is like, I don't know, P6mm or something. And this is a mosaic tiling at the Alhambra. So, these things are kind of like all over the place. And this is a project that I kind of succeeded in. I kind of like came up with a way to make these. So these are actually randomly generated from they're basically Gaussian random fields that have this kind of symmetry. And then all I did was, so it's like a function that's coming out of the page. And then what I did is I just used a kind of a cute like color map for contour F in matplotlib, right? And it makes these, made pretty pictures. Then fast forward a little bit to 2023, and I got involved in this kind of big NSF institute. It was kind of, sort of machine learning plus physics across multiple scales. And I met this solid state physicist named Elif Erdogan, and somehow, I don't know, at the bar or something, we wound up talking about this art project. And she says, the 2D symmetries of that thing are the 3D generalization of those space groups. We would really like to have functions that are invariant to those groups when we're trying to solve different kinds of sort of electronic problems in crystalline solids, right? And so there's all kinds of neat math around this, things like Bloch's theorem and so on, in which you'd like to be able to think about this stuff. And here was kind of like some machinery actually in the form of this art project for dealing with this, because there wasn't anything really specific about it to 2D. So suddenly this project went from kind of like being an art project, goofy sort of like, pandemic fever dream, to being an actual research project. And just to kind of give you a little bit of an idea of the difference between the kind of 2D case and the 3D case. So I made these little renderings of a couple of the space groups. And, so instead of like a 2D tiling, we now have like a 3D tiling. And I've put a little sort of asymmetric object in each one of these things. This is the set of kind of group operations up to translation. So it's not quite a subgroup, but it's kind of gives you an idea of how complicated some of these things could be. There's 230 of them, 219 if you don't account for handedness, or you don't care about handedness. And so this became a research project. So like, let's, so then it became time, okay, well, let's formalize what we're actually doing here. And so rather than just showing you pictures, like we can sort of think a little bit more concretely. So plane groups and space groups, what I'm calling crystallographic groups, they're subgroups of the isometries on R2 and R3. As I said, there are sort of reflections, rotations, glides, inversions, of course, translations. And in 3D, you also get a thing called a screw, which is kind of like a glide, but it's a rotation and a translation at the same time. They're interestingly different than the kind of groups we usually deal with to represent symmetries in machine learning, because they're not finite and they're not compact, right? So usually when we think about like point group symmetry, like we might for molecules, we have a finite group or a Lie group that's like, compact. Here, it is neither of those things. And so the usual kind of thing we do to just sort of like sum out the group probably isn't going to work. Another thing to note is that they are not, in general, simple sort of semi-direct products of the translation group and the associated point group, okay? Some of them are, and those are the symmorphic groups, but most of the space groups are non-symmorphic. So anytime you have something like a glide or a screw, you're sort of not in the point group anymore. So it's not like not a simple sort of semi-direct product. So generally speaking, I'm going to here be denoting the group G acting on generally some RD, and we're going to assume we have some compatible basis. And what I mean by that is just that these correspond to Bravais lattices. The Bravais lattices don't allow for all arbitrary basis, like lattice basis vectors, and let's assume that you have one that's reasonable. A key object we're going to be thinking about is our orbits, and in the group sense. And when I write an orbit OX, what I'm saying is this is like the image of X, of the point X under the group, right? So all the points are kind of like equivalent, like the same part of that little F across all of the tiles. And maybe, as you might expect, right, the set of orbits corresponds to one of those tiles, more or less, and and it partitions sort of all of RD. All right, and generally speaking, when I talk about that little tile, I'm going to call it like the fundamental region, although I think material scientists like to call it the asymmetric unit. So the game we're trying to play here is we're trying to identify and build, like parameterize, functions that are invariant to these kinds of groups. And so invariance, right, is just this property that if we have some function, in our case from RD to R, when we apply the group action to X, right, we just get the same value back for F, and that needs to be true for all X and all G. Another way to think about this is that we're really kind of just defining a function that is, that's like a function of the space of orbits, right? So every orbit gets its own unique value. And it's not that hard to come up with functions like this, right? Because we could just define a function, restrict it to one of these fundamental regions, and then tile it, right? And that would of course be invariant. The trick is we want to do that in a way that's continuous, right? That respects the boundary conditions across these the edges. That is to say that even in so a space group in one dimension, right, is just like a periodic function. There's two of them, periodic and mirror, and then translate. And so this function is periodic, so it's invariant, but it is obviously discontinuous. Whereas good old sines and cosines and things like that are both continuous and invariant. Okay, so we want to kind of generalize things on the left versus things on the right. In pictures, the way to think about it is what we're after are things that look like this and not like this, right? So this is a function that's invariant, but you can see we get these like hard edges across the boundaries of the tiling. Whereas what we want are things like this that are invariant, but are like smooth, like you can't kind of just see where the tile ends. And that shouldn't be super surprising too, right? Because actually the tile itself is not unique. And so if we can kind of see where the tile is, then probably that indicates we kind of have like screwed something up. So these are just kind of three different examples for these three different groups, just to give you an idea of kind of what is the game that we're playing. In 3D, it's a little bit harder to see, but we're still trying to think about the same thing here. So These guys are, so there's a contour plot. This is continuous, doesn't have these kind of sharp boundaries, right, that we're getting there. In 3 dimensions, you can see it a little bit more clearly, where we get these discontinuities across these things. So how do we construct stuff like the thing on the left? But before we talk about how to do it, let's talk about why this is an interesting thing to do, why we might want to build machine learning models that have these kinds of properties other than just like making pretty pictures. And I think there's a couple different motivating reasons to do this. I'm personally most excited about it and spend most of my time thinking about the kind of solid state physics problems. So specifically, right, we think about something like, if we're imagining solving the electronic Schrödinger equation for a bunch of nuclei that are fixed in a lattice, right, so that the potential, right, is an invariant function, then those group operations commute with the Hamiltonian, and that's a thing that we would like to kind of see in our solutions as well. And in particular, lately, there's been some exciting work in thinking about neural nets as ansätze for solving the Schrödinger equation, so Fermi net, things like that, if you've heard of that. And it's very exciting, but of course, generally speaking, we'd like to have the right symmetries built into something like that, because these things can be very floppy, and so they tend not to scale. You might hope that if we build in the right kind of invariance, the right kind of symmetry, that they would be less floppy in the right kind of way, and maybe we could sort of go bigger and better in terms of like the number of electrons we can handle. More generally, and I realize there's a lot of hand-wringing about whether or not invariance is a good idea at this workshop, and it is an open question, to be sure, but my point of view on the sort of trajectory of deep learning is that we kind of should have called it invariant learning, and not, the depth is great, like yay depth, and composition matters, but if you really think about when deep learning has advanced, right, it's been unlocking like one invariance at a time, right? So the original success, you think about like AlexNet, that was about ComNets, right? That was about translation invariance. MLPs are, they're fine. MLPs are fine, but they're not actually like particularly good. They're not really better than other kinds of machine learning models you might fit. They have different operational regimes. They're different. They're appropriate for different kinds of problems. But as function representations, there's nothing really sort of magical about them. And then we think about, I don't know, the next, or kind of a concurrent success, right, was speech recognition, also taking advantage of translation invariance. Graph neural nets, right? It's about generalizing that notion to local structures on graphs. Think about transformers, all the stuff that's going on. It's kind of a permutation invariance. And so the history, in some sense, in my mind, is that kind of once we figured out how to build the right kind of structure into things, that's when things got good. Now, this all, as we've seen, kind of gets blown up in different ways as people have scaled up. But I'm sort of buying into that view for this. But beyond quantum mechanics, I think there's lots of other kind of interesting things across multiple different scales. I've been excited about mechanical metamaterials, for example, for a while, and I view them as kind of interesting sort of mechanical analogs to neural nets. These like sort of massively parametric, flexible structures, and it's natural to think about periodicity in the representation and parameterization of those things. Of course, we also like to think about this kind of periodicity at larger scales for things like architectural structures, and then also things like additive manufacturing, where it's nice to think about infills and different kinds of patterns and isotropy and other kinds of mechanical properties that you might want to have when you're doing this. And so these groups kind of come up in a lot of different places, and it'd be nice to be able to represent them in our models. So I'm very motivated by this. But I'm actually going to wind up mostly talking about this kind of like at the end, mostly because I don't have the results are still pretty preliminary for the quantum stuff, whereas I have pretty pictures for the metamaterials. Okay, so this project turned from a sort of an art project into like a proper research project, and I pulled in my good friend and collaborator Peter Orbans, who's faculty at the University College London. And this is a good moment to mention something that's important, which is that there's not a student involved in what I'm going to talk about for the first 2/3 of this talk. This is just me and Peter doing this, and so so it has a little bit of a different flavor, and also moves very slowly. But if like there was a code written or a theorem proved, it was Peter who did it. But what I'm going to tell you about is 2 different approaches to building these kinds of functions. The first part is going to be a very sort of like applied math kind of spectral graph theory view in the world. And then the second is going to be a very machine learning-y kind of thing. And it's kind of like, how would we build a neural network that can that has these kinds of invariances? And they're going to be interrelated and kind of use some of the same machinery. And the main object that you want to think about and that we're going to be trying to build is a thing called an orbifold. All right. And so this word should sort of call to mind the idea of this, like the manifold of orbits. And that is to say that every point on this surface is like one of the orbits, and it is folded up in the sort of right way to satisfy the boundary conditions associated with these groups, right? So really what you want to think of is that it's like every one of these little edges is glued to one of the other edges, or maybe glued to itself. And then so if you did that gluing, then it would go from a two-dimensional object into some higher dimensional object, and that's what we would get. So in this case, we get this like kind of pillow. That's also why it has some finite number of kind of like cusps associated with it, because these are like the rotation centers and things like that. So that's one for P2. This one I think is kind of winds up looking like a little canoe or something. That is P2 and G. And then P3 is a little bit more complicated. All right, so if we had access to this object, then we would sort of be able to do interesting things with these groups. We would be able to kind of like compose with a map representing these and kind of reason about locality via this orbifoldy object. All right, the way we're going to get at that orbifold is we're going to approximate it, and we're going to approximate it with a graph. And so the way we're going to do that is we're going to choose some finite set of orbits, and that corresponds to choosing like a finite set of points in that fundamental region. We're going to build a kind of like a mesh essentially on that, okay, representing some notion of locality in the graph. So we think of this as like an epsilon net. And you could do this by just sort of like connecting to every vertex within like, an epsilon ball of view, or in the k nearest neighbors, or whatever you like. The metric we do this under is the sort of like induced metric, in which it's like the Euclidean metric, but minimized over the group. And so what all that means is that if you are closer to somebody by jumping over the edge periodically, then that's the one that's closest to you. That's your distance from that other orbit, not the other ones that are sort of farther away. So you take that min. Generally speaking, doing a min like that will not result in a metric, but in the case of these beautiful isometries, it turns out you can prove that it does. So this is practically, right, what this means is you're sort of throwing down a bunch of points in the fundamental region. You're sort of tiling those around. Those points that you just put down kind of locally, you don't have to go very far, because you never have to consider any point that's farther than the diameter of your little polytope away. And then you build that graph. And so here's what it looks like for a couple of the wallpaper groups. This little red region is the kind of fundamental region we're looking at. You throw down some points in this using, however you want. And you then tile those points around, okay? So you apply kind of local group actions to each of them. And then you build your little epsilon net, right? So then you connect to your nearest neighbors or whatever. Yeah.
I had a question. This kind of reminds me of like the constructing like a steerable group convolution, where you kind of use the regular like the weights kind of transform into the regular representation. Do you know if there are any?
I don't know enough about that to say anything smart. Sorry. But why don't you tell me about it afterwards, yeah. and maybe we can figure that out. Okay, so we're going to build. But what we're going to do is build this graph, and then this graph is going to kind of represent our sort of discrete notion of locality, and we can then use graph type machinery in order to construct this. And the first thing we're going to do is we're going to think about how we can use that to find the eigenfunctions of the Laplace-Beltrami operator on the orbifold. Now that sounds like sort of like that's like kind of a mouthful, but these are kind of like the generalization of the Fourier series or Fourier transform to sort of arbitrary manifolds, and so they're nice because they give us a complete basis, like a complete L2 basis for whatever it is we care about. And if we're sort of in the game of approximating difficult things, that feels like sort of a nice place to be. And the way to think about what the Laplace-Beltrami operator is just like the Laplacian, but on the manifold. And there's some like really interesting things that happen. In particular, so this is just the eigenvalue problem associated with that operator. And it's a positive definite operator, so we have non-negative eigenvalues, and because it's like a compact set, then we have discrete spectra. And I'm embarrassed to say that it wasn't until like kind of doing all this that I really fully appreciated like exactly what the connection is between the Fourier series and Fourier transform. You kind of learn these things separately, and that it just basically boils down to whether or not you have a compact set and kind of how you represent these things. So this is the problem. If we could solve this problem on the manifold, right, then we'd have this very nice basis that we could use to solve interesting problems. And what's neat is that we can approximate the Laplace-Beltrami operator with the graph Laplacian. So we have this graph, and the graph Laplacian is essentially, you can think of that as basically being like a finite differences approximation to the Laplace-Beltrami operator. And so if we were to do that and then compute the eigenvalues and eigenvectors of the graph Laplacian, then we recover some like algorithms that in machine learning are kind of like ancient history now, but and also recover some like essentially identical algorithms from the kind of more conventional computational mechanics. Yeah.
Eigenfunctions of the Laplace operator in these orbifolds, are those these sort of periodic functions that we ultimately are interested in by construction?
Yes. Yeah. They are the generalization of the Fourier transform, the Fourier series, basically for that. Yeah, and so if we have a way to get those, then those give us this complete basis. And I should have said a complete basis of functions that are all invariant, right? Each one of them is invariant as we go. Okay. So back in the early 2000s, there was a lot of energy put into the idea of manifold learning, and this is kind of what led ultimately to things like UMAP and stuff that people use now, which is like, let's come up with fancy and interesting nonlinear variations of PCA, essentially, right? Like how do we identify, how do we visualize high dimensional data? One of the sort of very interesting versions of that was an algorithm called Laplacian eigenmaps. And what Laplacian eigenmaps did is you took your high dimensional data, you sort of built a graph arising from like a k nearest neighbors, right? So you're assuming that in data space you can like look at how similar things are. You take that graph, compute this graph Laplacian, and then the eigenvectors of that graph Laplacian then provide, you could take like the first couple of dimensions of them, and that would give you an embedding for your data in low dimensions that somehow reflected approximated the locality in pretty well. And so this is something that people explored quite a lot, and then actually surprisingly recently there's been some work kind of exploring the theory and convergence rates of these methods. And this is kind of very close to what we're doing, right? We're building this graph and then looking at the, kind of doing some spectral graph theory to get these embeddings, or rather to get these functions. Yep.
The earliest attempts to define a convolutional graph neural network use essentially the same trick, right? They diagonalize the graph Laplacian and then apply the function on the diagonal.
Here you mean like Kipf and Welling?
No, like Juan Bruna.
Okay.
But Kipf and Welling use essentially an approximate version of that. If you were to choose the graph correctly, does this amount to the same?
I'm not building a graph neural network.
Okay, there's no graph at all, or?
No, there's a graph. I'm just not going to build a graph neural network.
So if you just apply functions to the diagonal basis of the graph Laplacian.
Yeah, the diagonal base. Yes, no, that's right. So the diagonal basis of the graph Laplacian is what we're after. And that's going to give us a feature representation that's invariant. Yeah,
so it's just like the way that the convolutions are defined, right?
Well, I guess in the sense that if we think of those convolutions as representing things that are sort of like invariant to transformations of the kind of the transformations represented by the graph, then yeah, I would agree. So what's also kind of interesting here, right, is that there's this like equivalent kind of algorithm from more conventional sort of like computational mechanics, sort of applied math, right? Which is where we're using like a finite difference method in order to solve the Helmholtz problem. It's different because now we're not given data. We're living in low dimensions. We have some manifold and we're sort of putting down points, building some mesh. But fundamentally, then we're still sort of solving the same kind of problem. So it's kind of fun that these ideas kind of appear in a couple different ways. And what we're doing here is just using them to try to represent these neat eigenfunctions. And so so we wind up with a relatively simple algorithm where we have some fundamental region. We throw down our points. We apply these kind of local members to build our net. And then what we're going to do is we're going to kind of weight the edges in the way one does with like Laplacian eigenmaps, and then compute the normalized Laplacian. Eigenvalue decomposition is probably very sparse, right? So we can probably, so this is not too painful. And then we wind up with a discrete approximation to these functions, and then we can kind of like interpolate between them in order to represent them. And there's a couple of caveats I should add to this, which is in general we have degeneracies, right? So we're gonna have sort of multiplicities of our eigenvalues, and so we're not necessarily going to get like pretty eigenfunctions this way. We're going to get eigenspaces. Also, I've ignored sort of in describing it the fact that we have to handle reflections a little bit carefully in order to because you kind of generally speaking, this machinery is about manifolds without boundary, and here we have boundaries. Moreover, we also have sort of a finite number of these like singularities where the curvature becomes infinite, and so our finite difference, we're going to expect that this approximation is going to kind of suck and converge slowly near those points. And more generally, because it's finite differences, the rate of convergence of Laplacian can be kind of slow, and moreover, we also have this kind of like annoying parameter we have to tune. But we get cool eigenfunctions that so these are sort of interesting interesting generalizations of things like Fourier series to these things. So each of these functions is is an invariant function, and and they kind of have like increasing frequency as we go. So the motivation here being like a nice basis that reflects these kinds of that sort of captures the right symmetries for these groups. And I'm also showing the eigenvalue, but you probably don't care about that. And it's it's kind of neat. Like, I mean, they look like these. They kind of look like you'd expect in some sense, in that they kind of reflect like rotational structure and so on.
Maybe a common question. So I guess like one way to think about these eigenfunctions is probably like resonant waves in these sort of geometries, right?
Yeah.
Once you count them, then they naturally kind of are periodic, right? In this case.
Yeah, that's right. I mean, this is
weird groups.
Yeah, I mean, there was this famous like, can you hear the shape of a drum thing? This is kind of like in the same general sort of vicinity. And we can do this with the space groups as well, and get these kind of neat eigenfunctions that we might use as sort of interesting basis for things, or as like the first layer of a neural network that we want to be invariant. All right, so that's the kind of like the applied math portion of the talk in some sense. I didn't do any machine learning there, right? I just sort of did a relatively straightforward approach to this. That's like what we think of as like a linear representation. If you want to have a linear basis, then this is a way you might do it. But now let's do it in a way that we can use with neural networks and, I don't know, decision trees or whatever you want. And the general sort of concept here is that if I wanted to make functions that were just periodic in 1D, right? One way I could do that is by generating some arbitrary unconstrained continuous function in 2D, so from R2 to R, and then I could think about like a circle, and I could think about the restriction of the function to that circle, right? And if I imagine going through this as kind of looping around the circle, right? So this is theta, and then I'm flipping around here, then I'll get a continuous function. So I can sort of transform a higher dimensional arbitrary function into a periodic function. And this is like a way we could build a neural network, a periodic neural network, right? It's like, and people do this all the time, it should be said, where you sort of take like cosine and sine representations as features, right? And then what does that do? Well, that's essentially giving you this like R2 parameterization. And so what we might hope to be able to do is generalize this trick broadly. And if we could come up with a map that, if we think of this circle as being kind of the orbifold, then if we can come up with a map from the space we care about to the orbifold, then we can define a function on that higher dimensional embedding space, and that the resulting composition of the map and that function will be invariant, right? Because the orbifold respects the boundary conditions, and clearly, if we're like continuous in this space, then the restriction is continuous, right? So, so this is the game we're gonna be playing, and what we're gonna do is we're gonna start with our orbit graph from before, but instead of doing sort of dealing with the Laplacian and looking for eigenvalues and eigenvectors of that, we're going to do something different, which is we're going to compute geodesics on it. Okay, so we're going to build a matrix of distances between all of our vertices, between all these orbits, right, that are representing, you know, locality via this graph geodesic, and we're hoping that's going to approximate a geodesic on the orbifold, right? And then we're going to use multidimensional scaling on that guy, right? So that is, we're going to sort of solve this eigenvalue problem, that the goal of which is to find an embedding into a higher dimensional space such that those distances are approximately preserved. Okay, so we're going into this higher dimensional space. We have all these distances, and the hope is that in the higher dimensional space, that kind of that structure is preserved. This turns out to be another classic machine learning algorithm called isomap. Yep. They are, yeah. So we get that graph, right, and then every edge has like a length, right, and then you're following, you know, you're finding the minimum distance on the graph between 2 points and looking at that distance. The reason we're doing it this way is so that we can accommodate the fact that the fastest way to get to another thing may be to go through some other weird boundary condition, right? And so that's what we're solving for here. So who's heard of isomap? Oh no. Anyway, so this is like a very famous algorithm, and I thought it was very famous. It used to be very famous, maybe. And it is doing this. So you have some high dimensional data, and what you do, you know, everybody's looking at like these tiny little data, but you know, what you would do is you would take your data set and you would you would build this same kind of graph based on nearest neighbors. You compute that geodesic between all of your data. And so this has the property that if your data live on some weird manifold in high dimensions, then if you could follow the manifold around to get to some of the other data, then that feels like kind of the sort of data respecting metric. And then once you do that, then you do this MDS in like 2 dimensions, and then you get a visualization that you can look at. And so this again is kind of like a predecessor to things like t-SNE and UMAP. We're doing something, we're kind of abusing it in a funny way, which is that, you know, it was invented to deal with the case where we have sort of like high dimensional data and we're trying to go to low dimensions. Here what we're going to do is start with low dimensions and actually go to a higher dimensional space in order to represent things. So we're actually kind of blowing up the dimension in order to get this orbifold embedding. But once we do that, that's actually how I make these pictures, is we can take these things and blow them up, and they 3 dimensions may not be the right number of dimensions for them. You can see that like this guy like self-intersects, but it allows us to take those points and you know, take a dense set of points in the fundamental region and figure out exactly what kind of object we would like to have that would sort of glue together all of the edges in the right way. And I'm just doing it here with these little 2-dimensional things because, unsurprisingly, for the space groups, we wind up with like, you know, 6 to 8-dimensional objects that are very hard to reason about, which is also why, you know, you can kind of look through, you know, the kind of pure mathematics literature of various kinds and sort of find, you know, people reason about Klein bottles and things like that that are kind of what some of these groups correspond to. And for 2 dimensions, people have come up with, I don't know, names for all these things, pillowcases and whatnot. But in 3 dimensions, nobody has any idea what they look like because they're much higher dimensional objects. And so they sort of haven't been categorized in that case. But what we have here is an algorithm that just produces it computationally and represents it for you without you having to think about it and give it a weird name. So what we get then is this map from, say, R2 or R3 to this higher dimensional space that is itself invariant to the group action, and we call this a maximal invariant because, you know, the way to think about it is basically every point in R2 then maps to the, you know, if it's on some orbit, it maps to the same point in this higher dimensional space. But what this lets us do is if we define say, a neural network or whatever you want on that embedding space, and you compose your neural network with the map, with this orbifold map, you get an invariant function to that group, right? Because it's a function of this embedding space. So it's like the circle trick, but with some more complicated object.
Doesn't this sidestep some of the controversial discussions, if you will, about whether or not applies to the neural net? Because you're doing a neural net space on a completely different representation.
Yeah. It totally potential. One might hope, right, that we can.
The neural net itself has no equivariance invariance.
Yeah, that's right. The neural net is just defined on this higher dimensional space. Yeah, so you could make that. You could make that a big spaghetti mess of MLP or whatever you want, right? Yeah. All right. So, so the way I kind of think about what we're doing here, right, is we're taking. I mean, kind of the way I think about kind of what we achieve with this is imagine that we start with the orbifold in this higher dimensional space, and now what you do is you spray paint it. Okay. You spray paint it with whatever your function values are going to be. And then when you unfold your spray painted thing, you get something that if you tile the plane with that, your spray paint pattern will sort of be continuous, right? Because when it was folded up, it had the right boundary conditions. And of course, we could cut this up in different ways too, which is its own kind of fun sub-project here, which is you get these crazy tilings if you want to. But it's kind of I think of this as being kind of the way to think about what that embedding is doing. I can kind of do anything I want in that higher dimensional space, and it will result in sort of continuity respecting structure when I unfold it. So we can do this with neural nets. We can generate a random net and plot the neat functions you get, and they're weird neural net functions that respect the space groups, and so we can look at that in sort of 2 or 3 dimensions, and get these kind of interesting structures. These are just random, right? So this is not, there's nothing. I'm not fitting to anything there, but some people around here like Gaussian processes too, and things like support vector machines, if you remember what those are. Occasionally, these things are still useful, and so one thing we can do is build positive definite kernel functions out of this orbifold. So that is to say, some function that's positive definite just means we give it some evaluated at some finite set of points. Then the matrix that we get from that is positive definite, and we use that for lots of different kinds of machinery. And what's neat is that, kind of unsurprisingly, composing both arguments with our orbifold gives us an invariant kernel function, right? That's invariant in each argument. Yeah, and this is just kind of if you think about the kind of kernel trick view on this, right? It's just a featurization now. So an inner product of a featurization that's invariant. So of course the inner product is invariant. And so you can do some wacky things, right? So this is just sort of for fun, but it's thinking about what does a support vector machine look like with this decision boundary look like with this kind of kernel. And on one hand, it's silly, right? Nobody has data like this. Nobody cares. But on the other hand, it's kind of cool because I feel like it shows the power of why invariance is interesting, right? Where this decision boundary, this feels like a complicated decision boundary for a small number of points. But because of the structure that we're imposing, right, it's able to generalize all over the place. When it sees one point, it's effectively seeing a copy of that point everywhere else, right? So even though this is kind of silly, it's also kind of interesting in telling us why is invariance interesting. But let's forget SVMs. Let's talk about Gaussian processes. So we can do the same kind of thing, and as I mentioned earlier, that circle trick, actually, my PhD advisor 30 years ago sort of introduced that circle trick to derive a periodic kernel function for things like Gaussian processes. And so here we're kind of generalizing that. We don't have a nice closed form, but we can still evaluate these things and get these neat Gaussian fields. We can also think about what the sort of what the correlation function looks like. And so here I'm clamping one of the points and then looking at kind of what points does that correlate with. Unsurprisingly, that's another invariant function. But again, it's kind of revealing the interesting structure and kind of what do you learn about the space clamping one of the points. Do that in 3D as well. And again, we get these kind of neat invariances. We draw random functions from our Gaussian process, just like we could draw, make our random neural networks. And this is how I like what I was actually after originally, which is like being able to draw from these Gaussian processes, plot them with some kind of like, non-trivial color map, and like get something that kind of looks neat. So these are like actual draws from a Gaussian process with this contour map, which I don't know. I had this idea that you get like custom fabric made, so you have like completely unique things. Every single one of these is like a random seed determines like what thing you get today. So I think these are kind of fun. And of course, more generally, we can construct all kinds of things. We can get like sub-level sets of them to define solids, right? We can define densities this way. We can do kind of, build these kinds of interesting objects. And so this kind of picture should, if you care about charge densities and things like that, right, should kind of get your mind going. Another thing you could do is we can define Markov chains that leave things like Gaussian processes invariant, right? And so we can, in particular, we can define Markov chains that are sort of highly correlated, right? That sort of move slowly through the space of like these sort of Gaussian draws. And then we can plot those, and you get these kind of like trippy functions. So what we're basically just looking at correlated samples from this from these guys. Yeah.
There isn't any way to interpolate different orbifolds, is there?
I wish there was, but I don't have a nice way to think about that, because that would be, yeah, if it actually moved between different groups, yeah, I don't have a good way to do that. At least not yet. I can move between, yeah, different draws from a single one. And of course, we could also be modifying the basis and stuff if we wanted, but yeah, I don't know how to do that.
Could you at least play with the sort of hierarchy, because some of these are subgroups of one another?
Yeah. So yeah, there probably, yes. I think the answer to that is that the orbifold those orbifolds must have some interesting relationship to each other. I have not spent any time thinking about it, but I think that's a case where you kind of could expect it to work, where you're basically kind of unfolding the orbifold corresponding to that subgroup in some way, where you're sort of basically there's some edge, right, or something that's kind of coming apart, and you get this like approximate symmetry breaking, and then it really becomes that group. So something like that should work, but I haven't done it. Oh yeah, here's one more. All right. So how are we doing on time? 15 minutes. Okay, so so this has been kind of fun. But one thing that's neat about this kind of like orbifold approach is that actually returning to the eigenfunction thing, you can do a much better job of solving that problem using the orbifold, it turns out. And this is because of things like jacks. So the graph Laplacian was annoying, right? Because it's a finite differences approximation to the second derivative. Yeah. And so that's bad, because finite differences is terrible, and also second derivatives are kind of they're kind of messy. But what we can do instead is we can construct some linearly independent basis in the higher dimensional space. So think about, I don't know, just throw down a bunch of Gaussians or polynomials or whatever you want in the like higher dimensional space. That's going to induce a basis that's invariant in the original space, right? Now, this is not like an interesting orthogonal basis or anything. It's just a basis. And what I can then do, though, is say I'm going to approximate the eigenfunctions in that basis, right? And so basically what I'm doing is setting up like a Galerkin method, right? Sort of Rayleigh-Ritz approximation to these guys, where I just have to sort of find the, I basically just have to compute two kinds of inner products, the inner products of the basis functions. Now, here we're operating in like R2 or R3. Inner product of those guys, and then also the inner product of just their gradients. No second derivatives to be found. And here, this is just like Green's theorem, by the way. I'm not doing anything fancy. And I get a generalized eigenvalue problem that I can solve. And so it's only one derivative, and I can use jacks, right? I can just differentiate through my orbifold into that basis set to get these two guys. And these are relatively low dimensional integrals, right? They're just in 2 or 3 dimensions, so I can use quadrature and it'll work. And then I get those matrices, I solve this guy, and I get way cleaner sort of versions of these eigenfunctions. I'm not going to show you them, but this is kind of it won't surprise you that sort of that by getting rid of finite differences and second derivatives, that we're sort of like in a way nicer sort of computational regime. All right, so with the time remaining, I'm going to tell you about a project that uses some of this machinery to do something fun, which is thinking about symmetry-constrained mechanical metamaterials. So these are going to be things that exhibit those kinds of symmetries in 2 dimensions and result in kind of interesting behaviors. And so a metamaterial is some kind of object that has interesting sort of properties that are arising from its geometry rather than its material composition. So this is what is called a cellular solid. So this is where we have these pores, and the shape of the pores results in kind of interesting differences in behavior, whether it's like buckling, or this is what we would call like auxeticity. So this is like it has like a negative Poisson ratio. So if you don't know what that means, usually you take some squishy thing and you press it down and its sides expand, right? Well, here, if it's a sort of a non-physical thing would be if you squish it down and its sides contract. That would be surprising. That corresponds to a negative Poisson ratio, which is not a thing we sort of generally see in nature, but that you can get through by kind of constructing interesting geometries. And this is work, I should say, with actually involves people who can do work, unlike just professors. So Moran is my postdoc, and Anne is Katja Bertoldi, who's an applied mechanics person at Harvard, who is more or less responsible for all these awesome things existing. Anne is her postdoc, and so this has been a kind of a little bit larger collaboration. But so the game here is cellular solids, as they have been studied, all just have P1 symmetry. Right, so they just have they're just like a grid of cells, and you think about the shape of the cells in order to do the interesting thing. Yeah, you might say, well, let's come up with like a much richer set of possible cellular structures by considering all the possible groups. Rather than just P1, let's have like all of them, and parameterize that set and see what we might get. Can we get more interesting things? And somehow, like, this is like intended to be the kind of like complete set of possible things. Now, I've been sort of presenting all these things with, kind of talking mostly about kind of like level sets and contour functions as the way to approach things. But that actually turns out to be not a great way to tackle this kind of problem, because it can wind up with non-physical designs, right? Because there's no reason that a level set of a function is going to be connected. And of course, if we're going to actually make this object, right, it needs to be connected. So if you think about the black here as being like the material, then these things hanging in space, right, are not going to make sense as part of a metamaterial. And that's what I would get if I just took like a sub-level set of this thing. So moreover, when we do this kind of mechanical metamaterial optimization, we'd like to be able to specify some volume fraction. That is to say, we want to have a certain amount of sort of empty space in this thing, because different kinds of stress-strain relationships, you might be able to just get them by putting more material down. So the interesting geometry generally arises in like topology and shape optimization by sort of constraining what volume is available. It's not obvious how to do that with a level set. And so, we sort of explored like a variety of kind of ways to try to regularize this out, try to enforce physicality with this. And then in January, in my group, so we have like a physical lab space with some like, laser cutters and 3D printers and stuff. And so we had this kind of day where we thought it'd be fun to just people to come in and bring art projects and different kinds of things. Cindy made this like amazing laser cut dragon. And I had this idea that finally I was going to take this machinery that we developed, and I was going to make like a piece of art. And I'm a woodworker, and so I got these veneers. And the idea was to laser cut the veneers and then, in this pattern, and then frame it and make this thing. And I realized, though, that if I had these disconnected things, like I would have from level sets, that I was going to be spending my entire life gluing little pieces down on the thing. And that was very motivating to think about a mathematical solution to constrain this out. And so it took me a little longer to make this than I expected. So this thing is about, I don't know, it's like this big. And because I decided to develop sort of a way to solve that problem that would preserve the contiguity, basically, of the sort of topology of this thing, so that you always wind up with physical structures. And by the way, that then when I'm gluing them together, I only have to glue like one big piece. And the way that it works is to, rather than define an invariant function, define a flow that leaves invariant functions invariant. Okay, so if you start with like an invariant structure and you flow it, that it preserves that. It preserves that invariance. And so this turns out for space groups to be like not quite equivariant. It's like, I kind of refer to it as like kind of like quasi-equivariance, which is to say that you apply the group action, and on the sort of outside of the function, you only apply the point group, sort of subgroup of the action. So you don't apply the sort of the whole thing, and particularly don't apply the translations. And that gives you the right kind of flows that preserve the structure. Also, what's neat is you can do this, of course, with neural networks and things, and we can make them, can make them divergence-free. I'm not going to tell you how to do that right now, but if you're interested in divergence-free neural networks, I can tell you a trick to do that after the talk. And so we can come up with these things that allow us to start with some simple pre-specified structure that's nice and physical and that just corresponds to kind of the fundamental regions, flow it through our equivariant-ish neural network. We get some new structure that has the same volume that it had before because it's divergence-free, and also preserves kind of the, sort of preserves the physicality of this thing. And now we have a flexible way to parameterize these solids that is always guaranteeing these nice properties. And so we can then, and then additionally, we have a differentiable continuum mechanics simulator that we developed that I'm not going to explain, but that uses things like implicit gradients and stuff. But we can then we can use that with this pipeline to then say, for example, I want to achieve some particular stress strain curves, and I choose some group, and I can sort of backprop then all the way into this vector field, this neural network vector field, which is essentially parameterizing the shape and giving me group symmetric objects that achieve those stress strain curves. And you can do some pretty crazy things with these that are kind of surprising. This I really like because it's actually really weird. So this is the shape that's undeformed. If you squeeze it, it doesn't expand or contract. If you stretch it, it also doesn't expand or contract. So it has 0 Poisson ratio in both tension and compression, which is an interesting property. And you can kind of see that because it's P6, what's happening, right, is it's like rotating. It's sort of rotating down whenever it is compressed and kind of rotating out whenever it's expanded. And so this is kind of like an example of behavior that would be very hard to get with like a P1 conventional cellular solid. And so this is some other examples. And then these are actual frames of video from physical realizations of these guys. So this is like simulation on the left, targeting particular Poisson ratios with, in simulation, backpropping into this thing. On the right, this has been laser cut out of rubber and then stretched and measured with an instrument machine. And what's neat is that they look, basically that our experiments actually line up interestingly well with the predictions from our simulator, and that it actually kind of exhibits the behavior that we expected in our design. So here's a little video of one of these being stretched. So on the left is the simulation, and on the right is the video of the actual thing. All right. So I'm just about out of time, so I'll wrap up here. So these plane and space groups kind of come up all over the place. It's fun to think about how we might build functions and machine learning models that have the right kind of invariance, because they seem like they might be useful for a lot of different kinds of physical problems across different scales. It's challenging because unlike most of the groups we deal with in machine learning, they're infinite and not and only locally compact. The method I told you about today centers on building this idea of an orbit graph that we're using to approximate this orbifold object. And I told you about sort of one approach that's a kind of a linear approach, very sort of applied mathy, in which we use a graph Laplacian to get at these eigenfunctions. And then another approach that's very machine learning-y, in which we construct an object that we can compose with things like neural networks, with a bonus approach that is doing the first thing using the second machinery and having it kind of be a little bit nicer. And then also this kind of fun like symmetry-constrained stuff. We're exploring these in a lot of different other contexts as well that I either didn't have time to talk about or that we're sort of not done with enough to discuss. But thank you all for listening. these are the collaborators on this project. So Peter, of course, has been involved in this whole thing. Aleph is involved in all this quantum mechanics stuff that we want to do with this, and is the reason I even know about any of this. And then these folks were, sort of drove the symmetry-constrained mechanical metamaterials work. So thanks all for listening.
Hi, thanks for the great talk. I was wondering if I guess kind of your last part, I think, led to this question, but have you looked at like phase transitions between materials, like going kind of interpolating between these like different space groups or point groups and phase transitions?
I haven't, but it's a really interesting question.
Yeah,
to raise,
I might be interested.
Yeah, happy to chat. Yeah.
Are you all looking at space groups for the metamaterials?
So yes, but the simulation of the space groups is much more painful. So our differentiable simulator in principle works in 3D. I mean, it's basically isogeometric analysis implemented in JAX, and it would, mathematically yes, but it would take ages. And so I think the approach we want to take for the three-dimensional metamaterials is to actually take more advantage of the periodicity. So here, I didn't explain kind of how we actually do this, right? But basically, what I'm doing is sort of relaxing the invariance as it gets near so the vector field drops off to 0, basically near the boundaries, so the boundaries are preserved. And but what you could do is just identify the thing that's unique up to translation, like some, kind of the unit cell, and then represent the periodic boundary conditions in like finite element analysis. And then in principle, you could then maybe scale up to 3D because you'd be able to tackle a much smaller object. And if you care about, here we're kind of thinking about like homogenization, right? So we're thinking about these like macroscopic properties. And so you might reasonably think then actually it would be even better because then we get rid of the boundary effects that we're getting here. But so that's the attack on that. And then that's without talking about how to make it either, by the way. But maybe we could 3D print it.
We'll be excited to see some of those things.
It should be like rotates and all kinds of stuff. Yeah.
Thanks, really interesting. So is it cheating to use rubber here? Because it can deform under stress and you're like shifting the unit cell. And would this deformation experiment work with solid materials?
That is an interesting question. I mean, from a simulation point of view, it's just like what's your Young's modulus and Poisson ratio in the underlying material. And so I think and it's just a statics simulation as well, right? So I don't think it's cheating because in principle, we could do this with steel. And if you could compress it, then it should have the same behavior. It's just that that's really hard to make. And so cutting it out of sheet rubber is a lot easier.
Thanks. I may have missed this, but so what's the logic for laying down the points on the unit cells? And what is the criterion for those points and sort of the place?
Yeah, the criterion is that you kind of want a dense mesh because the fidelity of your orbifold construction is essentially just a function of how well you're representing that locality, right? So so you pay, either way you do it, you're doing an eigenvalue problem. And so, roughly cubically, you're paying in these points. And so there's some trade-off between kind of how nicely are you representing the continuity across the boundaries and that notion of locality versus how much you're willing to pay to construct it. The good news is you only have to do it once forever. That is to say, there's 230, you do it, I can just ship you the weight. So there's 230 times you ever have to do this. And so in principle, then you should never have to think about that very hard. Also, in principle, you could just do that, find the embedding, and then train a neural network to represent that map if you wanted to. And then, and kind of do it that way.
Great, thanks a lot.